Hi everyone, this video is down for the International Conference on Wireless Technologies Embedded and Intelligent Systems 6th edition, which will be in Fez, Morocco between 40 and 60 October 2020. So this presentation is presented by Dr. Abdelatif Slimani from Faculty of Science and Technology, Fez, Morocco. Intelligent Systems Research and Renewable Energies Laboratory. So, in this presentation, we will talk about the development of an ultra-wideband hybrid coupler with adjustable phase shifter for 5G applications. So, to understand our work, we will use this plan. So in the first axis, we will talk about the context of work, definitions, some definitions, objective and frequencies band. And second axis, we will talk about the design and results. So first, we talk about design structure, and in the second, we will talk about result and discussion, simulation results. So, and we will finish by a small conclusion. So hybrid couplers. So hybrid couplers are structures which can give equal power split between the two outputs, okay, coupled and throughout ports. So with well-defined phase shifts the difference between these two output ports, while the fourth port is strictly isolated. So in general, in state of art, we have two popular hybrid coupler. The first, which presented in figure 1, which has 90 degrees phase shift between output 3 and 4, and the second type is presented in figure 2, which has 180 degree phase shift between output ports. So in the first figure we have the first input, and we can see that we have two input ports and two output ports. So the first input is for input power, and the second input port is isolated, and we have two output ports, and in these two output ports we can calculate the phase shift between them, which equal 90 degree. So for the second figure, we have the first input, and the second input is always isolated, and we have two output ports 3 and 4. So between these two output ports we have 180 degree phase shifter. Okay, so with these couplers we can see that are the single integral component that we can use like divider, which has input and two outputs, or we can use it like combiner. We have two inputs and one output, or we can use it like a frequency duplexer. It depends on frequency in output. Okay, so our objective in this work is to design just one single hybrid coupler, okay, so which can work for 90 degree and 180 degree phase shift. Okay, so we have just one single input, so we have just one single hybrid coupler with two phase shifts. Okay, so the method used to conceive this hybrid coupler is based on localized damped elements like diodes. Okay, so our frequencies band, can see that the first frequencies that will be used by 5G is expected from 2020 will be those under 6 GHz between 3.4 and 3.8 GHz. Okay, so this band is close to that of 4G at 2.6 GHz and of 3G at 2.1 GHz. Okay, so for us we choose the resonance frequency of 3.0 GHz for 5G. Okay, fixed for 5G, and the bandwidth from 3.5 GHz and 4.5 GHz. Okay, which respects the norms of ultra wideband characteristic. So design and results. So figure 6 represents the equivalent circuits of our hybrid coupler before 3D design. Okay, so here we have a lot of impedance and we have two diodes, okay, the first and the second. So to find the best structure of our hybrid coupler, we need to know the best impedance here. So we have Z0 is known is 50 ohm, and we have Z1 is known. So the impedance, important impedance here is Z2. Okay, so if we know the exact value of Z2, we can conceive our hybrid coupler, and we can obtain the best result of our hybrid coupler. So after calculation of this impedance, we go directly to three-dimension conception of this hybrid coupler, which represents in figure 7. Okay, so we have two input ports and we have three output ports. So first port is for input power, the second is isolated, and the third and the fourth and the fifth. So in general we have just two inputs and two outputs. Okay, so if we need to have 90-degree phase shift to activate diode number 1, okay, we switch on this diode and we switch off this diode number 2. Okay, so this port is turned off. If we need to have phase shift of 180 degrees, so we activate diode number 2 and we turn off diode number 1. Okay, so in general we have just two inputs and two outputs, and two outputs that it depends on the phase shift, desired phase shift. Okay, so to understand the method used to calculate the impedance value, you can see our work published in microwave and optical technology letters. Okay, so here we have the detailed calculation of this hybrid coupler. So design and results and discussion results. Okay, so the first case when diode number 1 is on and diode number 2 is off. So figure 8 represents S parameter in HFSS software, and figure 9 show these parameters in CST software. So for return losses, we can see that our in our ports 1, 3, and 4, we can see that we have a best matching in around our resonance frequency. Also, transmission coefficient is around 3 decibel around our resonance frequency 3.8 gigahertz. Also for CST, we can see that we have good matching in around our resonance frequency, and we can see that we have also transmission coefficient around 1.3 decibel around our resonance frequency. The second case when diode 1 is off and diode 2 is on. So also here we can see that we have return losses, we have best matching for return losses. Okay, and 110 decibel around our resonance frequency. Okay, and also the transmission coefficients are around 3 decibel for the two case in HFSS and CST. So here our important work is here. So we have the phase shift for 90 degrees when diode number 1 is on and diode number 2 is off. So here we can see that we have a phase shift between ports 3, 1, 3 and 1, 4. Okay, in CST or in HFSS. Okay, so in CST in red color and HFSS in black color. So we can see that the difference between output 3 and 4 is around 90 degrees, and when we turn off the diode number 1 and we turn on the diode number 2, we can see that the phase shift pass from 90 degree to 180 degree for both case of CST and HFSS. Okay, so we can see that when we turn on diode number 1 and we turn off diode number 2, the phase shift is around 90 degree, and when we turn and when we turn off diode number 1 and we activate diode number 2, we can see that the phase shifts pass from 90 degree to 180 degree. Okay, so here we have a comparison between loss coefficient, isolation, and coupling factors when diode number 1 is on and diode number 2 is off in figure 40. Okay, so we can see that isolation is 110 decibel, okay, around our resonance frequency for the first case, and the loss factor and coupling factor is around 13 decibel around our resonance frequency. Also, in the case of diode 2 is on and diode number 1 is off, we can see that the isolation is under 110 decibel and the coupling and loss coefficient are around 3 decibel. Okay, so as conclusion, so we can see that in this work we have developed one hybrid coupler for 5G application, which can switch fast shifts between 90 degree and 180 degree. Okay, so the developed coupler shows excellent fast shifts of 90 degree and 180 degree depending on the case of the diodes turn off or turn on. Okay, so the design of this hybrid coupler is very robust and easy in fabrication. It can be utilized in many ultra-wideband 5G applications like radars and satellite employment. Thank you for your attention.